Good morning. I am Andrew White, Process Valve Business Development Manager with the Lesman Instrument Company. Thank you for taking the time to attend our webinar this morning. Our topic is control valves versus regulators. This webinar will be recorded and posted to our website for anyone to listen to later. Please enter your questions in the question section of the menu bar. We will answer those at the end of the presentation. I'm pleased to announce our speaker for today's webinar, Harry Woebkenberg. Harry is Vice President of Jordan Valve. He has responsibility for the Jordan Valve and the low flow valve brands within Richards Industrials. He's been with Richards for 15 years and originally started in the industry in 1980 with Zelmox. Harry, please proceed with your presentation.
Okay, Andrew, thank you for the introduction and thanks for inviting me to participate today. We're going to talk about control valves versus regulators. What are the advantages and potential disadvantages of each? And hopefully by the time that we pop out into this, everybody has a decent idea of the key considerations when solution for whatever your flow needs. So what is a control valve? A control valve is the final control element in a flow loop. A control valve is most frequently used to control the following variables, those being pressure, temperature, flow, level. There are basically two types of control valve. One would be linear, and we're going to focus primarily on linear type control valves today, but they're typically globe style valves up to 6-inch, but some manufacturers offer to 24 inches and beyond. So these can get pretty significant size-wise. Automated ball valves and butterfly valves to 12 inches, but in my prior life, I've seen them go to 100-inch and beyond. So again, there are several types out there available. But again, for the purposes of this presentation, we're going to focus primarily on linear type control valves. Typical pneumatic control valve consists of a diaphragm actuator, a positioner, a side mounted positioner is the most globe style body and plug, and the inherent flow characteristic is generally either equal percentage or linear. And again, that's the inherent characteristic. What's in a control loop? Here's a very bog standard view of what are the elements in a control loop. As most of you may know, a lot of control loops can be much more sophisticated than the little that I'm showing here. But you can see the final control element, which is the control valve. The flow goes through the control valve. It goes to the measuring device. The measuring device calculates the difference in the actual flow versus the desired set point. It sends a signal back to the controller. The controller then will communicate back to the final control element, and the valve will either open or close based on what we need to do to achieve the desired set point. So again, very simple, but that's basically how a control valve or a control loop works and where the control valve fits in the control loop. What are the advantages of a control valve? Highly accurate positioning and repeatability. Accurate within 0.5% of the desired set point. I've got 0.5 PSI in there. That's a typo. I apologize for that, but it should be within 0.5% of the desired set point. So extremely accurate. A wide range of pressure classes, sizes, materials of construction, and configurations. high temperature capabilities can be provided with specific flow characteristics. Control valves have the ability to handle high pressure drops. You have the ability to select your failure mode. So you can select fail open, fail close, fail last, and that can be on failure of air or failure of electric, but you can select the failure mode. And in a lot of cases, you can choose to have noise reduction or noise mitigation and some type of cavitation control as part of the control valve as well. What are the limitations? Well, you can do all that neat stuff with it, but as a result, there's added cost and complexity because you're not only talking about the control valve itself, but you're talking about all the elements that are part of the control loop. There's a requirement for auxiliary systems. Need air, you can need electricity. So those are additional considerations. Friction in the stem packing, guides or seals introduce deadband. Bit of emissions can be a concern due to the rising stem. So if a nasty medium, potentially you could drag emissions up through the packing and they could escape to atmosphere. Speed of response is limited by the other control loop elements. So even though this is, you know, the time involved is extremely fast, it is slower than some other options that you may have. And the results do not always justify the costs. So what we're going to explore today is, you know, do you need a control valve? Do you need all the bells and whistles? Or potentially, is there a simpler solution that may provide the results that you desire or require? And you know, what are the things that we need to consider? How can, you know, what considerations can we make to make sure that we choose the absolute best solution for your process needs? I love this quote. I don't know how many in the audience may be familiar with Hans Baumann, but Hans Baumann was is a pretty interesting guy. He's a German American inventor, professional engineer, writer. But he is a big time control valve guy. And the fact that he is, that's why I find this quote so compelling. Properly utilized, regulators could replace control valves in at least 25% of all control loops. So, you know, here's a gentleman, you know, as an inventor, he was with Cashco and he invented the Cashco Ranger. He was with Mason Elin and he did the Cam Flex. Many of you may be familiar with Baumann control valves, and his most recent venture is Hanbay, and it's electric motor operators. But so he's held a lot of positions in the valve world, along with being a contributor to the control valve primer. So Hans Baumann is, like I say, he's a big time control valve guy, but he's saying that, you know, if you properly apply a regulator, a lot of times, you know, it can work as well for you and be a more economical choice than choosing a control valve. So what's a regulator? A regulator is a standalone mechanical self-actuating pressure controller. So basically, if we talk about a control valve that's controlling pressure to some desired set point and all the elements of that control loop, a regulator can do effectively the same thing in a much simpler design. But we're going to get into, you know, your requirements and your needs And that's where you're going to be able to make a good choice. Do I want a regulator or do I want a control valve? So the regulator is a proportional controller. Here you see a globe style regulator, and you see it has a spring, it has a diaphragm. Our regulated variable or our controlled variable is going to be P2, or our downstream pressure. So let's say, for instance, we're coming in at 100 psi and we want to knock it down to 60 psi. This is self-operated. You don't need air, you don't need electricity, you don't need Bubba out there to stroke the valve. All you need to do is set this and forget it, and it's going to work. And what you have is a force balance mechanism. The P2, or the downstream pressure, goes up underneath the diaphragm, and the diaphragm acts against the spring as a force balance. So the pressure underneath the diaphragm, this is a pressure reducing valve. So it's going to be in a normally open position. So as the downstream pressure comes up to the set point, what it's going to do is compress the spring and take the regulator to the closed position. As the downstream pressure falls below the set point, the spring will overcome the pressure underneath the diaphragm and go back to the open position. So it just, again, you set it, you forget it, and it will just go out there and merrily regulate for the rest of its effective service life. And you can see here, in a control loop, we had a pressure sensor downstream of the valve. We had a controller, okay, that was going to send the signal to back to the feedback mechanism, which in this case is the valve plug. So this does all the things that a control loop does in a very simple, elegant package. So you can see here how they work. Again, in a pressure reducing valve, the springs keep the PRV in the normally open position. We're controlling P2, or the downstream pressure, and the downstream pressure is sensed up underneath the diaphragm, and you have the force balance between the spring and the diaphragm. Typical regulator applications, systems requiring control within 2 and 30% of set point. Now, if you recall, we said that the control valve with a positioner can be accurate within 0.5% of the desired set point. Here we're talking anywhere from 2% to 30% of the set point. So one of the important considerations that should jump off the page at this point is that you're not going to get the accuracy in a regulator that you're normally going to see in a control loop. So that's one of the things that we need to keep in mind. The set and forget functions. So you see a lot in utilities. You see a lot of regulators in steam, plant air, industrial gases, water, so both hot water and chilled water, lube oil. There are regulators that can handle differential pressure requirements. Vacuum, temperature control, tank blanketing regulators are used a lot. Tank management and managing the vapor space in a tank, and various back pressure relief functions as well. So there are a lot of places where regulators can be effectively applied. The picture here, I'm an old guy, so I would know what this is, but this is a steam calliope on a steamship. And you can see there's a regulator here that's regulating the pressure, regulating the steam that goes in, and they use the old steam calliope on the paddle boats down on this one's out of New Orleans, but they use those to play music. For those of you who may not be familiar with something like that. What are the advantages to a regulator? no external power is needed to position the valve, okay? We call these self-operated or direct operated regulators. No need for separate measuring elements or feedback controllers. Designs tend to be simple. They're lower cost generally. They're highly reliable and in most cases very easy to maintain. Absence of stem packing eliminates external leakage and a source of high friction when you're stroking the valve. And regulators are force balanced with a controlled variable and offer very fast response. These respond off of the line medium itself. So again, respond very quickly to changes in the system. The controlled media must be relatively clean and benign as materials of construction are limited. The clean is still a huge concern, as is the case with most control valves. But you know, in the recommended installation, we would recommend that there's a strainer upstream of the valve, because whether you're using a globe style or a sliding gate style, if you get something wedged between, you know, in the seat, they make for a very expensive strainer. So, you know, we don't want that to happen at all. But materials of construction, those now, you know, a lot of companies will actually manufacture regulators using high alloys. So it's uh, not a standard, but you know, we will make them out of Inconel, alloy 20, Hastelloy. So you know, if we can source material and we can machine it, we can make a regulator out of it. So materials of construction aren't as limited as they once were, but most of the time you're going to find regulators primarily in ductile or cast iron, carbon steel, or stainless steel. Uh, Operating points are not constant due to droop, and we'll talk a little bit about droop here in a minute. And that's droop is the inverse of accuracy, and that's what we're talking about here, generally speaking. Regulators cannot accommodate noise reduction or cavitation control trims, and failure modes are fixed. As you saw in the couple of cutaway drawings a couple slides back, pressure reducing valve is in the normally open position. So the failure mode is going to be fail open. A back pressure regulator, a self-operated back pressure regulator, is normally in the closed position. So the failure position is going to be fail closed. So you don't get a choice here, as you do with a control valve. Now, accuracy of regulation, or droop, also called proportional band or offset. That's the deviation from the set point as flow increases through the regulator. So if your set point is 100 psi, and at some point in time the pressure, your set pressure drops off to 90, we're going to say that there's 10% droop, or the inverse of that, 90% accuracy. So in a pressure regulating valve, the pressure falls below the set point, as in the example I just gave. The inverse in back pressure regulating valves is buildup or gain. So as you get to the point where you can't get any more flow through that back pressure regulating valve, you're going to see an increase or a spike in pressure. Lower the droop, the more accurate the regulator. And manufacturers will typically specify ranges from 2% to 30%. You say, my, that's a big range. Well, the reason that we talk 2% to 30% is there are different types of regulators. The least accurate and the least expensive are self-operated regulators. And those will generally provide accuracy between 70 and 90%. So say 10 to 30% droop. When you get into piloted and dome loaded regulators, they become more accurate and get significantly closer to the same performance that you'll get out of a control valve. This is a standard droop curve. And your regulated pressure, you have a set point. And again, if we want to say that that's, 100 PSI, you can see that as you flow, you start to droop off as flow increases through the curve. And then you get to the point where you're just not, you have virtually no control anymore when you get so full open. Generally, there are ranges that we'll talk about that you want to operate in that provide the best performance in regulators. This is just I always enjoy tossing this in here, but this is actually the calculation for droop. And there are three big considerations in droop. And one is the spring rate, the lighter the better. One is the effective diaphragm area, and that is the larger the better. And the last is stroke length, the shorter the better. So if you have short stroke, a big diaphragm, and a light spring, your droop performance will be pretty good. If you don't maximize the spring rate, if the diaphragm's on the smaller side and you have a long stroke, your droop performance is going to be pretty dismal. So that's just a calculation, the back of the napkin kind of calculation for droop. The self-operated regulator, and what I'm going to show you now are some actual droop curves that were run in the lab, and there are literally hundreds of data points here. But you can see in a self-operated regulator that, as flow increases, you start to droop, and boom, all of a sudden you're gone and you have no more regulation at all. But this is the least accurate of the different type of regulators that we're going to touch on today, and that is a self-operated or a direct operated regulator. The three different curves. The top curve, you can see where that's relatively flat. Pretty good regulation, actually. Pretty good pressure regulation. And then it's off. But what the difference here is it's a valve that has a very short stroke length. The diaphragm area is large yet commercially viable for the valve, and the spring rate is optimized. So you have a set point at right around 30 psi, and you've got a spring rate that's 10 to 30. So this is a valve that's optimized to minimize droop and increase accuracy. The second one has a heavier spring. So you can see here you the 30 to 95 psi spring, so you cover the set point, but you can see because of the heavier spring, you don't have the accuracy that you have in the first curve. And then the last one is a different valve type that has a longer stroke and a spring that's not optimized. So you can see that the droop performance there is not nearly as good as the first two. So again, this is a globe style droop curve, just to show you the regulator accuracy hierarchy. Self-contained or self-operated or direct operated, manufacturers will claim 10% to 30% droop. Piloted regulators, which means you have a pilot valve that's communicating with the main valve. It's a little more sophisticated, a little more complex than the standard operated valve or the direct operated valve. And it can be accurate within 5% to 10% of your set point. And a dome loaded, generally, end users will use air pressure to dome load, although you can put a hydraulic signal on, or you can put for instance, some other kind of gas where you load, and those tend to be very accurate because we're removing one of the variables from the regulator or from the droop equation, and we're putting a static signal on top of the diaphragm versus the spring. So they tend to be very accurate, coming in between 2% and 5%. And as you recall, we said that a control valve, very accurate, can be within 0.5% of the set point. Self-operated, simplest type of regulator. We talked about the fact that it's a force balance mechanism where our regulated or controlled variable is P2, or the downstream pressure, and it holds a specific downstream pressure or the set point. Size for optimum operation between 30% and 70%. So you're going to size a regulator just like you size a control valve. You put in a sizing program and it's going to tell you, hey, this is the CV you need, and so you want to put that in between 30% and 70% of full open, and that will give you your absolute best performance in a self-operated BPRV. Operating in that range will minimize droop and maximize accuracy. And again, self-operated, generally speaking, you're going to be accurate within 10% to 30%. Pilot operated, you can see here that there's a pilot valve. So you've got a regulator that's going to communicate with the main valve. Okay, so small pilot capacities in large diaphragm surface areas, generally speaking, people will choose a piloted pressure regulator when they need greater accuracy than a direct operated regulator, or they need higher flows, or both. And you can, to optimize the accuracy here, you can actually run this between 10 and 90% of the rated flow. So this gives you, you're going to have greater turn down, greater rangeability in a pilot operated regulator than you are going to have in a direct operated regulator. And it maintains a pressure on top of the diaphragm accurate within 2 to 10%. So very accurate, much more accurate than most direct operated. So you can see here the flow curve. You can see that we're dead flat here for quite some time before it starts to droop off. So you've got a much wider range that you can operate in and maintain the accuracy of regulation that you require. Dome loaded. This is a dome loaded, and you'll immediately notice that, you know, hey, it looks like this guy's chopped off. Well, we don't have a spring housing here because we don't have a spring. So you're going to be able to put a load on top of this, and because it eliminates the spring, the droop is greatly reduced. We generally talk about somewhere between 2% and 5% of the set point, which means it's between 95 and 98% accurate to your desired set point. You put an air signal across the top. In order to do that, you'll need an air regulator, or you can do it with an IDP. To optimize the accuracy, again, you can run this between 10 and 90% of the rated flow. And here too, you have rangeability that's somewhere between 35 to 1 and 50 to 1. One thing about both the dome loaded and the pilot operated, you do need a sensing line with both of these. So the sensing line is going to sense your controlled variable, okay, which again, we're still going to control our P2 or our downstream pressure. And you can see the little pipe plug here underneath there where the diaphragm is housed. But and then you'd want to make that sensing line as short and straight as possible, so you don't have any turbulence in that line and don't get any false pressure readings your control variable. Okay, and here again you can see dead flat, similar to the pilot operated valve. You can see that there's quite accurate in the regulation. Okay. So the hierarchy of accuracy. Control valve with a positioner, we talked about first. That's generally accurate within 0.5% of the set point. In the optimum range, you can operate within 5% to 95% of the rated flow. A control valve without a positioner, accurate within 2% to 5% of the set point, and you can operate from 10 to 90. Dome loaded, very similar to a control valve without a positioner, 2% to 5% accurate to the set point, operate 10 to 90% open. Pilot operated 5 to 10%, 10 to 90% open. And then least accurate would be a self-operated regulator, operate within 30% to 70%. So the essential distinction here is that a control valve with a controller in positioner is capable of virtually eliminating offset when operating conditions depart from the original set point. And regulators are proportional controllers, generally controlling within an accuracy of 2% to 30%. Okay, so again, there's that's the big thing. It's one of the big questions is going to be how accurate do you have to be, and that's going to depend. Some systems have to be extremely accurate, and others not so much. In utilities, for the most part, those generally speaking don't have to be as accurate as applications actually inside a process. Final control element, you can see here just a control valve. This is a 2-inch carbon steel control valve with a positioner, and we're going to look at the cost versus a self-operated regulator. And again, understand that we're going to have much greater accuracy in this control valve with a positioner than we're going to have in a self-operated control valve. But the valve itself is $2,200 more for the control valve than it is for the regulators. Then you have to add in some other ancillaries, transducers anywhere from $300 to $1,200, controllers anywhere from $500 to $1,500. So your all-in pricing, a self-operated pressure reducing valve, a little over $4,000. Transportation and installation, you're all in for about $5,000. Control valve with a side mounted positioner, transducer, controller, transportation and installation. Total, you're a little bit more than twice the price. So again, self-operated regulator, you're going to be 85% accurate. Control valve with a side mounted positioner, you're going to be considerably more accurate, 99%. So the essential questions are, what accuracy of control is required? The installation cost parameters. Do you have power or air available? Is rapid response or special application a consideration? What's the line size and material? Do you have noise and cavitation concerns? And is a predetermined failure mode required? So all of these need to be answered, as you go through and select the best product, the best solution for your application. And the big question is how much am I willing to pay for accuracy? So, you can see, and the cost can escalate. Those were very simple examples of both. But again, it's just a matter of, how deep how big's my checkbook, and what do I really need to do in order to have a good solution for my process requirements. So that is it for the presentation part. If we have any questions, we'd be happy to try to field those now.
Yeah, thank you, Harry. So we do have some questions coming in. So the first question, it was stated that control valves may have fugitive emissions due to the movement of the stem. Does this mean that control valves cannot be placed in sterile processes since the stem is in touch with the environment and it will make it back into the process?
Well, okay, this is, I do more on the industrial side, but we do have we do have a valve division called SteriFlow. So the SteriFlow product does not expose any medium to the environment, and so it doesn't drag anything. There's no egress, there's no ingress on these particular valves based on their design. So if you have the proper valve, you can absolutely use a control valve in sanitary applications. So and again, that's not in my area of expertise, but I do know enough to know that there are valves especially configured for those kind of applications. And if you have any questions, the folks at Lesman can certainly help you out there. And again, that was kind of a non-answer. I apologize for that, but absolutely, we can. The folks at Lesman can help you find an appropriate product for that type of application if that's a concern.
Okay. The next question we've got is, where does a motor-operated control valve fit in the hierarchy of accuracy?
Oh, that's a great question. Generally, we're seeing more and more requests for motor operators, and generally speaking, they're actually going to be more accurate than a positioner, than a valve with a positioner, and a diaphragm actuator and a side mounted positioner or top mounted positioner or whatever. Because what happens is you take all the mechanical vagaries out of out of the equation. You no longer have linkages and some of the slops and tolerances that come on the mechanical side. Now, again, you're pretty darn accurate with with a control valve with a positioner, but motor operators, the corrections are more minute, and again, they take out all the mechanical vagaries, and there are fewer variables involved. So it's going to be even more accurate than a pneumatic control valve with a positioner.
Okay, thank you. We've got, looks like just one more question. Last question is, how do I choose between equal percentage and linear inherent characteristics in a control valve?
Oh, wow, that's another great question. Most control valve systems give the best performance when they behave in a linear manner. So, your inherent characteristics, that's the characteristic that comes from the factory. Okay, it's tested in a controlled environment, and it's either going to supply a linear characteristic or an equal percentage characteristic as it takes the full pressure drop across the valve. And since when you bring that valve out into the field, you put it into a process, there are going to be other things in you're going to have elbows and you're going to have T's and other things that are going to take up some of that pressure drop. And again, since you want to perform in a linear fashion, if the valve is taking the majority of the pressure drop, you're going to want to choose a linear inherent characteristic. If there are several elements in the flow that are taking part of that pressure drop, you're going to want to have an equal percentage inherent characteristic, because that equal percentage is going to move that curve, that inherent curve is going to move more towards linear acting, than it would be just being tested on a bench. So again, if you're taking all the pressure drop across the valve, choose linear. If it's taking it over various components in the piping system, then choose an equal percentage, and it will act more like a linear curve.
Okay, very good. And I don't see any more questions, so I'd like to thank our presenter, Harry, for taking time to present to us, and thank you to all the attendees. If you have additional questions after the webinar wraps up, you'll see my contact information as well as Harry's contact information on the final slide of the presentation. So this concludes our webinar. Thank you for joining.
Great, thanks.